Okay, so we're doing lesson 13. Let's start with 1A. Um, so they created a scenario where you have a primer, um, TAG, TAGTCCAATGCAG. And then what happens is the primer is attached to an annealing site, so it's attached to the strand of DNA, and then that's not PCR. Our DNA polymerase is going to attach to it and start building a new strand of DNA. But we're doing PCR, so we have our dd-NTPs in there, and they want to know what the binding pattern will look like on the gel after the PCR is over. So what you got is we have this new strand of DNA written out here because it's complementary. It's complementary to the RNA DNA polymerase. What happens is wherever there's a G, the DDGTP will attach there and stop termination. And not every time, so it'll allow it to continue to grow up to here, if possibly sometimes. Anyway, so in the one with DDGTP, you'll have bands here, here, and here with those G's. In DDHP, there'll be bands with here, here, and here with those A's, and so on with T and C. Okay, and then so that was for part A. And then B. So part B says, suppose I use E. coli DNA polymerase during the sequence reaction instead of Taq polymerase. And so if you do that, the polymerase 1, it cannot handle the high levels of temperature for PCR, so it'll break apart and the reaction will not be able to occur successfully for PCR. And for C, suppose you accidentally add DNA helicase instead of, well, no, actually everything else is there, but DNA helicase is there as well. So what happened is DNA helicase will break apart in the high temperature, but since all the other components are there, the reaction will still occur normally. Then in D, so you have 4 test tubes, one with DDATP, and the other they are supposed to have your C, G, and T, but they were not added. Now the other regular DNTPs are there, but the DDNTPs are not in the 3. So in the DDATP one, you'll have the normal thing where there'll be a break there. But the other 3, that will not occur there. So there'll be full strands of DNA in the other 3 test tubes. And that brings us to number 2.
Yes.
Yeah, feel free.
Do you have it?
I do. Well, you might want to use yours. Mine may not be complete.
Okay.
Yeah.
Okay. So, Okay. So 2A, we have tag polymerase synthesis and annealing. Oh, you're just getting my mouth. For B, we have AMPR and restricting enzymes. For C, we have positive electrode. For D, we have the 2' and the 3'. E is transformation. F is IPTG and XGAL. That's number 2.
All right. So for number 3. Okay. So in number 3, we have 2 strands of DNA, and we have 2 primers that attach to each one. And then for part A, write the single-stranded DNA sequence that you would use for the 2 primers. So they want us to say what the primers are going to be. So we said that the primers attach on the 3' ends, assuming we assume that it's just the bold area,
Yeah.
right? Okay. So on the bottom one, it's going to be starting with the 5' end. It's going to be G A G C C T T C A C T C A G T C, and then on the other one, the top one, it'll be the same thing, but for the starting with the 3' end on the other one. It's just the reverse of whatever the bold one is on the 3' end. Then B. So it talks about this equation that we use to determine the annealing temperature needed for PCR, and it's based upon the number of the percentage of nucleotides that are G and C, and also the total length of the primer. Yes. So they want us to calculate the temperature for the two primers needed for the two primers, and we said it was what? What did you say?
So what? This thing?
Yeah. What temperatures did you calculate?
62.27.
Yeah.
And 59.81.
Yeah. Perfect. Yeah. And then for C, so for C, it's 5' GC 3' and 3' C 5'. And then for D, so DNA A is does not need to be there because when you have PCR going on, the temperature is so high that the DNA separates on its own. You don't need the DNA A there to help it separate. And DAN does not need to be there because you're not trying to regulate the synthesis. You just want the process to happen as fast as possible. Okay, and that is number 4.
Yes. So number 4 is right here. So basically, I'm just gonna assume you can see that. We have this chart here, and then we have each of our base pair models. So we have 100, 200, 300, 400, 500, and then 1,000 over here. Then basically you just take in each lane every restriction enzyme that we have, and then we just match up the base pairs. So once you reach a certain number, then that's where it'll show up, and that's for A. For B, it's asking for a linear restriction map. And so we have, I know it's hard to see, these markers suck today, but basically we have 50 base pairs, and that's where the BAM high starts, and then 150 later we have eco rye, and then 100 after that we have Hein 3, and 100 after that we have BAM high again, and then at the end we have 500. And so then C is we have 150 to 100 and then 200. That's how we get to the next one, and that brings us to 5.
Okay. So for number 5, so for 5, well, it's only one part of 5. So first use you have to purify the mature mRNA. To purify the mature mRNAs. So here's what you do. So what happens is, so you take your strand of DNA from Saccharomyces. You take a mature mRNA from that organism, and then you purify the mature mRNA from cells and combine it with poly-DT primer. Then you add reverse transcriptase. What reverse transcriptase does is it takes a strand of mRNA and it makes a strand of DNA onto it using mRNA as the template. So it's reverse of what it normally does, which is why it's called reverse transcriptase. After that, you add DNTPs to synthesize the strand. Yeah, we have to add those at the same time as reverse transcriptase. Anyway, then you add RNase H to digest the mRNA. Okay. Then add DNA polymerase to synthesize the other strand. So you have the original strand, the original transcriptase maze. Then you have DNA polymerase that adds the complementary strand to that. So that's how you copy DNA from mRNA. Now you want to do the blue-white screening. So to do that, you insert it into a plasma vector using the right restrictive enzymes. You then treat both the cDNA and the vector with restrictive enzymes and mix them together. Then they are cleaved in the corresponding segments and covalently bonded by DNA ligase when mixed. Then we use a medium that is treated with ampicillin, IPGT, and xgal. The bacteria will begin to grow, and the ones that turn blue will be the ones that successfully contain the cDNA. And I was using the beta-galactosidase from the previous lesson. When it can synthesize something, it makes something that turns blue. But when it can't synthesize, it does not turn blue. That brings us to 6.
Okay, and so number 6 is just talking about the CRISPR thing, whatever. And so basically what CRISPR is, it's basically just a simple way to edit genomes. So for example, there's a sequence that we don't like because it's causing some harm or whatever. Then CRISPR allows us to take that segment and to cut it using Cas9. And then we can get rid of that, and then we can swap it in and replace it with a genome that we do want. And then the DNA will take care of itself from there. And so what we would hopefully like for it to do is that later on in the future we can cure all of the diseases that we cannot cure at the moment because we don't know what to do with them. And so if we can play with the genomes and the DNA, then it's possible that we can fix those diseases. And that's basically what that does. So yeah. Okay, where'd this thing go?
Yeah, I'll take care of it. Okay, bye everybody.
Okay, we're done.
We're done. Bye.